Hello. Hello, everyone, and welcome to my story about refactoring. But what is refactoring? It's the process of improving horrendous code like this into beautiful code like this, all while ensuring that tests still pass, code still runs, functionality is kept the same, and that the user doesn't suspect the thing. This could be by doing things like changing formatting, renaming variables, updating the structure, or using different algorithms and syntactic sugar. And today, I'll be talking about the story of refactoring a side project of mine that solves, annotates, and validates the minimum paths of this train game. Wow, I'm such a nerd. Anyways, why am I refactoring it? Well, I was a bit stuck and wanted some help from others. Not only that, but it was hard for me to easily make changes. And if it was hard for me to understand, well, it would have been even harder for others. Okay, so how did I get here? Well, often I'll have an idea that I want to implement, and Python is a great choice for doing so quickly. But as I added code, and more code, and more code, it quickly turned from a small script into an unmaintainable project. Do you want to see? No, I won't get you to read the entire code because you don't have to. In the same way that we can often just skim an entire article to get an idea of what it's about, like if we skim through this code, could we say that we have a reasonable idea of what it does, where to start, what's important, how it works, what it's made of? Quite long. Yeah. I know that my answer to that is no. But when I look at where I'm at now, I can very easily hazard that the project has something to do with graphs and annotations and stats and validations. But why was it so messy? How did it become like this? Well, because no one is perfect and can know exactly what all the future requirements will be, or know all of the syntactic sugar of a language, or know or identify when to use design principles and patterns, or have the time to make these changes up front, since with any piece of code, we can try our best to avoid these problems by having an idea for what to look out for, but often we need to stop and step back and take a look at what we're doing. Okay, so when we stop and step back, what can we do? Well, the first and easiest step that we can take is to use a formatter. It lets us take messy, long, condensed, and inconsistently written blocks like this, which don't even fit on the screen, and automatically turn them into this, which is much more human readable. Oh, it's probably a lot easier to tell in the formatted case that we're filtering a list, if I blur the examples, for example. And as an aside, I will mention that we can further fix this code by replacing this list indexing to retrieve the found item, by using next, which can be more efficient by not having to create an entire list. Now, in terms of formatters, there's a couple we can choose from, so we can spend a couple of hours researching each one and taking a look at what they do. No, wait, do we really want to do that? I mean, if our goal is to learn, then sure. But a good methodology to take away here right from the beginning is one about pragmatism. Because one of the biggest problems of refactoring is the amount of time it can take. It's important to realize when something is good enough. So if we're trying to be pragmatic, then let's just pick the first thing we find. I chose to use black. It's opinionated, but that doesn't matter to me. All that matters is that my code is always formatted to be readable and consistent, because in the future, trusting the formatter to automatically fix things and not having to debate with others is what will save us time. And if I do find issues, well, it will be very easy to swap out later because we can just run it again to reformat all the code. But even formatted code like this can still have issues because formatters won't tell us about code smells like problematic naming, like single characters, spelling mistakes like Celsius and Fahrenheit, or unused code like this last line that doesn't save the result anywhere. Or duplicated code, like these two lines that do the same thing, just to different variables. But a linter like rough will tell us all about these things. Linters are great because they can look at all of our code as we write it and raise issues for fixing that we might not be aware of. There's a whole list of them, and we don't have to follow all of them. We can even just silence the ones we don't like. But they'll often guide us into good patterns that we might have otherwise not considered. Like this warning I got about my function having too many arguments. Well, at first it made me think, that's silly. What's wrong with that? But when I took a step back and thought about how to address it, it made me realize what was better. If we take a look at the beginning, we'll see that there's a bunch of code, and some of that code loads some state into multiple variables. And when we take those variables and pass them into our function with many, many arguments, and then we pass those variables again individually into other functions, kind of messy. And while this is better than just having everything as global variables, just didn't really work. Instead, a better idea was to compartmentalize everything by putting these functions as part of a class. For example, by introducing a data holding class that lets me section off creating, storing, and loading the data elsewhere. So where I was previously passing around all of these arguments, now when I call my function, I only need to pass around this data object, making my code much simpler. What do we think? Is it better? Yeah? Is it the best? No, not really. But why? Well, let's take a look at this distance checking function. We'll see that we iterate over the distance list and get the port name. And then we'll iterate over all the distances to get the city name and the expected distance before then calculating the actual distance, for which we'll check against the expected distance and so on. But this isn't very intuitive code. What might make more intuitive sense is to go through every pair of nodes that we want to check the distance of, and then have a method from an object that calculates the actual distance, and then another that it retrieves the expected distance. And this is only great for readability, but it's also great for abstraction, because now all of these functions make it very easy to change the underlying functionality. For example, if we wanted to make optimizations by changing the distance calculation to use a faster algorithm, we can do that very easily. Because instead of passing around an object with data, what we really want is an interface to access particular kinds of data, showing the usefulness of designing around requirements. But what I had really done was apply some programming principles, known as interface segregation and dependency inversion, which both together dictate that functionality should depend on abstraction, not data that's been generated by some unknown entity. Or to put it more simply, it's easier to make spaghetti by mixing together cooked pasta and tomato sauce than it is to start from scratch with the raw pasta, the tomatoes, and the ice cream, which is for something else, I hope. And if you're curious for more, these both come from a set of 5 called solid. But if you're not aware of these principles, or you find them easy to forget, then I think a better methodology that I found useful to always tell myself is, there must be a better way. It might take some thinking, some research, or time to find what's available to make code simpler, shorter, and better, but I would have never gotten there if I wasn't always thinking about how to do better. Now that we've got a way to find issues in our code, we need a way to easily address them. And I found the easiest way to do that is to use an integrated development environment like PyCharm. IDEs like PyCharm are quite powerful, letting us out of the box easily do refactoring without any setup. I mean, look, it even has a refactoring menu. And some of the things I found quite helpful from this were renaming local variables, like here, changing port to port name, or renaming fields and methods throughout the entire project, and you'll see in updates everywhere else. It can also extract repeated blocks of code into a function. So these 3 repeated lines, we can just highlight them and then does it for us. Isn't that great? And it can also change the signature of a function's definition, updating for everywhere that it gets called. So here we add the parameter tracklist, and then just above, you'll see it's added the tracklist variable. That if it exists already there, it'll just simplify your life. It will also list usages, allowing you to quickly navigate between them, as well as go from this definition back to where it originated. And it can move files between folders, updating the usages and imports accordingly, which is probably much harder than something like Vim. And finally, show documentation. And I know what you might be thinking. Can't amazing lightweight editors like Vim and VS Code do all of that too? And as someone who's used both, I'm sure it could. But after I put on my pragmatic hat, I thought to myself, is it really worth all of the effort it would take to set that up when all of this comes out of the box from IntelliJ for free? Now, something I forgot to mention that an IDE can also do is help us with types. When we're writing small Python scripts, it might not be worthwhile to have types, but as our project grows, type hinting can become super helpful for quite a few reasons. One of these is spotting inevitable human errors. Like here, we route our code to explicitly expect a list, but networkx.paths returns a generator. So for example, if we save that function's output as a variable here, and then iterate over the returned value once, we'll get the expected output. But because it's a generator, when we iterate over the saved returned output again, nothing will happen since it's already been exhausted and can only be iterated over once, even though we might expect that from a list. But with the right tools, errors like this can be highlighted for us. Another case is when we're unpacking a nested data type. Here we'll see that the IDE can't give us any auto-completion help. But with typing, an IDE will give us auto-completions for that inner item, which is quite handy and lets you write code much faster. Okay, so now that we know all these types are important, let's go use them. But Evan, we might say, there's so many functions in your project, and it's going to be so much work given how large it is. And that is right. But we have technology, and we can automate finding and adding in types for us with a tool called MonkeyType, where for the following function, it can produce stubs annotating the return value and all of the parameters. And it will even update all the existing code for us as well. Of course, we don't need an IDE to benefit from type hinting, but once type hinting is all set up, it lets us run type checking tools like MyPy to ensure the continuous checking for types and errors. Oh, I forgot to mention again, typing is also really helpful for documentation. Take this function with no typing, for example. We have a vague idea that it's returning a connection path, and if we walk through it and try to annotate it, we'll see that there's a dictionary comprehension, so we'll annotate the function to return a dictionary. And in this comprehension, we'll see that we're iterating over this paths variable. So it's probably a nested list. And thus, it would make port and city indices to this list. But we still don't know what these edges that we're iterating over are. We just have to guess that it's some object in this list. And for our return dictionary, we also have to guess that it's just returning some position object from the function as a key, and also a set of directions as the values. And this sucks and isn't helpful because these objects could just be anything. These functions that claim to return positions and direction sets could also just return anything. In fact, or rather the code, lied to you. Port and city are actually names as strings, and paths is actually a nested dictionary. And if I continue to properly fill in these types, there's a much better idea that connection path is actually a dictionary mapping between positions to directions. And paths, let me make that more clear. is actually a 2D map of names to positions. And if I do some more formatting to alias the types, then we can set tuple int to a position, or, and this might be excessive, set aliases for the strings as well, both which make it clear what we're returning. Or better yet, we can use typing's new type that creates different string types, ensuring that we can't accidentally, for example, pass in a direction into something that's expecting a location. Setting up this excessive typing does mean that if they need to become classes, like after cleaning up the code, we could then just easily support that. For example, what is a direction set and how can we refine it? Well, a single connection from a port to a city has a direct path, but there's often multiple of these connections that can overlap, like this middle part here, meaning that the track at that overlapping point can consist of different components. In this case, a horizontal and an upright component, which I had just defined as strings and passed around as a set. Now, while this worked, it not only was difficult to understand, but also difficult to work with, since these directions were referenced and strings everywhere in the code. Part of this could be fixed by using enums, since they allow us to have identifiers that prevent us from making mistakes like typos. But another part of this problem still exists, since we always have to store and update these in a set to pass around, which can get quite finicky. Now, while we could create our own class to fix this problem, what does Python give us out of the box to help us here? Well, since our directions are made up of unique components, this could be analogous to a bitmap, where each bit represents a particular component, and when put together can be represented by a number. In fact, Python already supports this with the flag enum, letting us create single paths or combined paths, which we can then iterate over, or easily query their contents. Like here, we check if the vertical component is in a split path. How awesome is that? Now, previously, where we had a set of direction strings, we now have path components that are now clearer to understand, since they were never really directions, but instead components of a path. Okay, so what else can we refine? Well, let's continue with the renaming and cleaning up of some of these function calls. We can get rid of get, since it's not really Pythonic, and it adds extra noise and length to the code. We'll also update direction set of edge to be a path component of edge, representing the type that it's returning. And if we do that, we'll see that it's clearer, but we might also start to notice that our code is still a bit redundant, because our functions are named in such a way that mention the input and output type, even though that's already evident. What we could do instead is something like this, moving those functions onto the edge class instead, using properties, which we'll cover later. And if we look for more things to refine, the only thing we might be left with, if we follow those design principles, is putting this path data into an object, like before, and we could do even better once we realize that we're getting a connection path of two locations, both which fall under the same umbrella. Meaning that we can move this function into this paths class. But can we do better? I think there's one more place we can, and that's here in the edges function call, where we can make our code cleaner and safer using named arguments. I actually have the utmost adoration for Python's beautiful function argument system, so if you let me go on a tangent, I'll explain why. Take this example, this function that creates a rectangle. If we're using another language and we want to set up rotation to default to 0, then we often need to create a function override. But in Python, since we have default arguments, there's no need for chained overrides, because if we don't specify rotation, it will just default to 0 instead. Other languages fix this problem through builders that store and create this state, resolving this issue by allowing for optionally added data. But yet another issue lies due to the nature of the required ordered arguments, and that is that there's no knowing whether the arguments are set up correctly. You might have not noticed, but these arguments were swapped and should actually be width and height, not height and width, how I've had them this entire time. Python resolves this with named arguments, and thus also does away with builders, meaning that not only are functions self-documenting by having constant arguments labeled, but also our argument ordering is now redundant. Thus, by always using named arguments, our code is always future-proofed against errors. Like for example, if we go back to the default argument being used for rotation, we could call that function with arguments 1, 2, and 3, and the third argument overriding the default rotation of 0. But once we introduce a new required positional argument like opacity, where 1, 2, and 3 were previously for height, width, and rotation, they're now actually for height, width, and opacity without us ever knowing that this happened. Naming our arguments not only lets us prevent this issue, but also reduces issues with refactoring, such as in this case, where we want to fix the misordered parameters. We now don't have to make changes to reorder those arguments where that function is called. Now you might be wondering, what about the case where the name of the variable being passed in is named the same as the argument? Isn't that redundant and noisy? Well, yes, but maybe this is a good opportunity to rename the parameters. Perhaps it would be more descriptive to use names like from and to, making the code more natural to read. But then they might not make for great variable names inside the context of the function, or like in this case, where the from is actually a keyword in Python. If Python learned from Swift's named parameters, then we would be able to do something like this, which lets us specify both an external name like width and an external name like function. Internal name like function, sorry. But if we are stuck with something like our edges function that we want to clear up, our final choice is to use linters to check whether the parameter names match the variable names used in the arguments, allowing us to more safely go back to using positional arguments. If you are convinced by named arguments, then there is a way to force using them, and that is by putting the asterisk or star as the first parameter, or anywhere really. And what that will do is throw an error when we try to call a function without naming our arguments. But that can be cumbersome as it can be forgotten and can make the code messy and also require updating all the previous functions. And if you think there's a better way, you might be right, since we can use linters instead to just check and correct this for us. So if all this opened your eyes, come find me afterwards so we can contribute to automatically finding and applying these guardrails and enhancements. Anyways, now that we can see how named arguments can help with readability, maybe it's worth asking, how documented is your code? For example, let's take a look at this path validation function. From reading this, we can tell that this checks whether the path given is invalid by checking if two adjacent edges are on the same coordinate. But notice how this code was so messy that I had to walk through it to explain it. Maybe we could fix this by adding a docstring like checks whether two neighboring edges of a path are on the same coordinate. But is that really helpful? That doesn't really add info as to why that makes the path invalid. Plus, if the method ever changes, then the comment will be out of date and won't necessarily be updated. Instead, we could write something like checks whether a path loops onto itself, which isn't dependent on the method and explains that what we're actually checking for is that path what we're actually checking for is path with loops, and that's what's invalid in this case. Actually, while we're here, and I think running ahead of schedule, I noticed a few more things we could refactor. This invalid path function name is a bit redundant, like we mentioned before. So let's update it, removing the redundancy of path and adding is so that it reads more naturally as a verb. This length check is also redundant, since zip will return an empty iterable if any of the iterables that were given are also empty. So we can just remove that. Actually, it's not really clear what we're doing here either. For example, what does I and J mean? Let's update their names to edge and next edge to make it more clear what we're comparing. And on that note, the use of zip here also isn't really descriptive. Instead, we can use itertools.pairwise to make it more clear that we're iterating over the edges of the path pair by pair. And finally, this print statement doesn't really feel right either. Even though it's useful for information, such as for debugging, it would interfere with any output that our program might give. What would be better is if we introduced a logger and log this information using info, or even debug, allowing us to quickly do print debugging anywhere in our code while also giving us the easy option to turn them off later when we're done without having to delete them. Not forgetting also to update our F strings so that we're not performing unnecessary computation when we don't want any logs at all. But documentation isn't just about naming, comments, docstrings, or self-documenting type-ins. What I mean is, does it speak for itself through its overall structure? Like, how easy is it for someone other than you to pick up and understand your code with no context? If we take a look at what my repo would have looked like at the beginning, here's the GitHub page. There's no description. There's also no documentation or README for where to start. So maybe we'll have to just read some code. At the end of the day, that's where the truth is, right? But it's not clear which of all of these files are that code. And even once we find that file, it's thousands of lines long, and there's no main function to signify where exactly to start. If this was an actual repo, I probably would have given up my hopes of trying to use or contributing to it, which goes to show the easier that code is to pick up and understand with no context, the easier it will be for others to answer their questions or contribute without having to ask you. Now, in comparison, we could look up what we ended up with. Here's the main repo with only a few files. And if we scroll down, we'll find the README, which says that the entry point is the main file in the directory. And if we go to that directory, we can easily find the main file. And if we go to the bottom of that file, we'll find the main method. And then we'll see that the function being run comes from the helper. So if we go to the helper, we can now easily follow what comes next after update map. In fact, if we look at the entire structure as a whole, we'll see how all of these classes and packages made it much easier to reason about all the different components of the project. Not only that, but it embraces another important programming principle, this time the single responsibility principle, which says that everything should only ever have one responsibility. Why? Well, in the same way that a chef at a busy restaurant won't have time to make food, take orders, and handle payments. It's just not doable. And we can see the impact if we compare the main function from when I first started. It's quite long. And if we look at the files, what's the difference between graphing and graph? Well, if we take a look, graph is storing two data classes, one being quite long, when instead we could split this up into their own single files under its own folder. And this might be a bit of a concern given the extra imports and files to jump around, but that's just a trade-off to consider depending on our class length. Okay, now that we've started to update our code, what else can we do? Well, another good principle to follow is dry, or don't repeat yourself. Dry is important for so many reasons. Here we have some code that repeatedly calculates distances, and we could refactor it by first introducing a function for abstraction, and then by using that function to provide consistency, before finally introducing a for loop, making our code much cleaner and safer by providing safety through reassurance that everything is running the same way. For example, did you notice that there was a bug the first time I showed you this code? At the end here, it should actually be p3.y minus p2.y. Dry also allows us to be more efficient because now we don't need to copy or rewrite code to calculate distance. Or when we want to make changes like fixing a bug, or in this case, updating our logic to use the built-in hypotenuse method, we only need to do it in one place. And we can ensure that that bug fix or functionality is being used everywhere. But where did I apply it in my code? Well, one example is this validation code here that was being used in two different places. Our first thought might be to create a utils class, but this is often not a good idea as it creates a new dependency that incentivizes us to add more small functionality that there isn't really a good context for. Instead, this could be moved to be inside the validations module and renamed to be validate width. Or maybe what we should really do is ask ourselves, do we really need this? Maybe it would be better to just instead create a grid class that ensures that all rows are of the same width. Or maybe we should ask ourselves if there's a better way and to just remove the need for this entirely and instead just deal with the issue when it happens. Another place we could remove repeated code is during the annotations. In my map, annotations are what colors the path between a port on the left to a city at the top. And there are grouped annotations for both ports and cities. However, even though these are very similar, they're done by the same mechanism. We need to implement this slight difference since ports and cities are annotated through nesting. But conceptually, this is just recursion with a base case, and it made me think there must be a better way. So I ingeniously thought of this, which creates a nested list of specialized functions to be called with another generic function that could be used for both cities and ports and thus deduplicate our code. Did you get that? No. Great, because I quickly realized I didn't either. And while I learned that I could give myself a pat on the back for this ingenuity, what I really learned is that I should give myself a kick in the bum for all this added complexity, because sometimes using neat coding tricks to simplify code is not the best idea. And if it was, all of our code would be golfed to be as short as possible, and that's just not readable. So it's often worth considering, will the method of our refactoring really help? Or more importantly, and bringing up another principle, are we keeping it simple stupid? Our aim should always be to simplify our code and remove what might not be needed, not introduce added complexity. Eventually, I settled on a class like this that could be inherited and overridden to provide the extensibility that I was looking for. But was that extensibility something that I actually needed? Maybe it's worth consulting another principle. This time, Yagni, or you ain't gonna need it. Because should we really be refactoring for things that don't exist? Thus, I'll still always have a feeling that there must be a better way. Okay, but how can we be confident that we can make all these changes while keeping functionality the same? Well, isn't that what tests are for? In fact, having good tests is likely one of the most important things to have while refactoring. Because if we have tests to lean on, then we can make all the changes that we want, run our tests, and if they pass, then we're good to go. Tests aren't always the easiest thing to set up though, especially under added complexity. But even having very basic tests, where the program correctness might even be manually verified, is better than nothing. Since once that's done, it can be a starting point into automating it using integration tests, since with lots of refactoring, unit tests require too many changes. For example, this data class that takes in some file names and creates some state can easily be tested by an integration test. By just, as in our test, we could just create the file to test against, but it may become really hard to test the functions of a class like this, as different files would be needed to be created for every test. Not only that, but it's also not clear what's inside of these files. And if you haven't noticed, this is because it violates the dependency inversion principle. And the way that we can fix that is to instead change our class to be composed of this data, and to use the class method that would take in these file names and create the data needed to pass into the class. Now, in our code, we can continue to create the data using the file names, and in our tests, we can just specify the data that we want to be used, which makes things much cleaner. Now, while tests might ensure that our program stays the same, they don't really ensure that the program doesn't slow down. It's often not obvious when code can be slow, especially with Python, and more so when we're trying to ensure that we're not spending time in premature optimization. This is where a profiler like scaling can be quite helpful in analyzing the runtime of our code to determine where there's inefficiencies in computational memory. For example, this was the output I got when I noticed that my code started to be slow, and I couldn't figure out the change that I made that caused it. And here we see that the cause of this was in the creation of our coordinates, because I had set up my code in such a way to compute the values of a field on the class's creation, but edge nodes aren't really always needed. Instead, I could move this field to a function instead, only being run when needed. But maybe I wanted this as a property since it's nicer to read and implies that there's a value that shouldn't change. Well, we can do that with a property built-in decorator, which lets us return a function's output as a field. But a value shouldn't always be recomputed if it's going to return the same thing. This is where the functools.cache decorator comes in, which saves the output of a function so that we don't have to recompute it. This is great for values that we access many times, but only want to compute once. We could use both to solve this issue. However, this can lead to memory leaks, as the cache may retain instance references, preventing garbage collection. The solution is to use the cache property decorator, which does both in one go. Easily one of my favorite Python built-ins, and one that I found solved so many linter warnings as well. All right, now that's our profiling and optimization done, I wonder whether my refactoring story would be fast or slow if I profiled it. How much time we have left? 8 minutes. Okay, wow, that was quite a fun story. You might be wondering though, what about the profit? Did I get the help I needed? Yes, although there's still lots more to figure out. And while we could say that the profit is in saving time in the future, I think the real profit was everything that I learned along the way. And if you want to profit yourself, I've put up some resources here that you can reference later, and the slides will be here as well. I'll put up this QR code during the question time as well. But yeah, I want to say thanks to my partner and all of my friends for supporting me, and thanks to all of you for listening. I would love to hear any feedback that you have. I'm always trying to improve. And you can find me online at Kohilas or on GitHub if you wanted to take a look at my code. However, I won't claim that my code is perfect because I think there's always a better way. You can also find me in person here, as I think we still have some time for questions. Thank you. And I'll put up the QR code.
One, two. We do have a few minutes for questions. Yeah, we'll finish up at 12. Go.
Lord Andre first. Jeff, so far away.
Yeah, thank you for an amazing talk. Have you looked into using GitHub Copilot for automating some of these refactoring steps? And like, what's your opinion on just using AI tools for it?
It was, have I looked into maintaining or using it for refactoring?
Well, just using and kind of streamlining some of the refactoring steps that you mentioned. Yeah, just kind of like a scalpers.
Yeah, that's a good question. I have not. I should try it. I'm not aware that it can. I think it would be really interesting too. I think someone mentioned once that it'd be very awesome if tools like Copilot could do refactoring for you, and it would be a very easy, very awesome way of doing it, because then what you could do is you could just say, refactor this code to make it better, and it will do that. And then you have tests there, so it will just do it for you and then make sure that it works. And that also removes a lot of the need on us humans to have to do it. You could also say that maybe humans need to be involved because at the end of the day, we're the ones looking at it. But I think it could probably help with a lot of the structural things as well. But yeah, it's a good point.
Was there a question over there? Yeah. Here's a.
So, wife is my linter in life, and she, finds helpful little tips like when I park the car wrong or don't do the dishes right, and points them out, and it's very helpful. It's what we want, to quote you. And yet, ironically, we still have too many arguments exceptions, which I saw from your thing. And it strikes me that and so, linters frustrate me. I love type systems. I love, when I'm using them, I like tests. I like, solid. I'm not against these things. But do you think that there's a place for a scruffy language, and could that be Python? That it wasn't perfect, and that's okay, and it's not finished code. And if not, or maybe plus whatever, is what you're really saying that the future of linters is, to name a product, ChatGPT, and that what we're going to do is we're going to write random code, and it's going to be processed, all the diversity and humanity and difference and interesting stuff in it is going to be driven out to create, I'll bang on the table. Isn't that what there must be a better way? And is that what we want?
There was a lot there. Sorry, what was the main question? We can talk after, I think. Yes, I'd love to talk after.
Hello. I don't really know how your code fully works, so you're gonna have to help me out on this one. But
Yep.
When I was seeing your code on the board, it seemed like it was more functionally programmed, and near the end, it was more using object-oriented programming after the refactoring. How much more object-oriented decisions did you use at the end of the refactoring?
A lot more. Yeah. It's a good way of looking at it. I didn't really consider that.
Well, one of the main reasons I think this happened is because it is a game, after all, where you need to manage a lot of state with a lot of different objects.
It's the whole project is more like a tool that you add on top of the game. So there's not really much state. I think it could still be more functionally oriented. But the object-orientedness of it is just what helped make it more more understandable and more modular and split up. Yeah, that is something to think about, though. Did that answer your question?
Yeah.
Okay,
Thank you.
cool.
Awesome. One more question. Go ahead, David.
Coming from the data analysis side of things, when you first write your code and looking at a data set, you have an imperfect understanding of that data set. And as your understanding improves, you refactor. And I would be entirely comfortable taking at least 3 refactorings before I actually understood things. I'm just wondering if you have any comments on the actually understanding the data you are working with in relation to refactoring.
Yeah. So the data that I started with was data that I generated myself based on the existing game. I later learned that I did it in a very bad way. And that was not, I thought the game would never change again because it's quite an old game, and then it did, and then that broke a lot of things. Yeah, and I think the way I had structured it initially was by having a lot of, it was just a lot of JSON and a lot of CSV files and etc. And it was a lot of like one of those first examples was I have a really big data set and I have this ID that I'm looking for, and I don't have a map of the ID to the tile, for instance. And what I have to do is look through this entire list and then find the first tile that matches that ID. Obviously, that's not really the best way of doing it. And so even though you might start with that from the beginning, still better than nothing. And then once you realize that you are doing this kind of operation, then you can look at something into like importing all of these tiles as objects and then having a map with them inside of the code. Did that help? Okay, cool, awesome.